All right, so we're going to carry on today with chapter 5, but we're going to do something extremely interesting today. We're going to be looking at something called L'Hopital's rule, which basically is a way of calculating limits when it appears that we do not have a proper result because direct substitution leads us to either have 0 over 0 or infinity over infinity. And those are referred to as indeterminate forms because they don't give us any indication as to whether or not the function actually has a limit. Okay, so in other words, if you were to try one of these two, and of course, in the past we've used direct substitution many times to solve for limits. And so if you start with this one, you'll see that direct substitution leads us to uh, 0 over 0, which is of course not what we want. But that doesn't mean that we can't find the limit. It just means we have to try something different. All right, so yeah, of course, if you plug in everything here, so you get 2 minus 2 over minus 1 plus 1, and of course that's 0 over 0. So again, this is referred to as an indeterminate form. There's more than one kind of indeterminate form. But L'Hopital's rule is specifically meant for two special cases. Okay, now the other one that we can address with L'Hopital's rule is infinity over infinity. So both of these are indeterminate forms. Let me write this slightly differently. Okay, so in other words, they're both indeterminate forms. So the first case that we're looking at here, direct substitution leads to 0 over 0. So now sometimes there are algebraic techniques we can use to avoid this problem. Here, for example, what they've gone ahead and done is a little factoring. And of course, you might recognize that x squared minus 1 is x plus 1 times x minus 1. If not, you can use long division, and you'll see that x plus 1 is actually a factor of x squared plus 1. So that means this can be rewritten as two times x minus 1. So in other words, the original limit can now be rewritten as the limit as x goes to -1 of 2 times x minus 1. And now all of a sudden, instead of 0 over 0, we have -4. So that's fantastic. All right. Now, this function, by the way, let's look at this function as symbol. You can see there is a discontinuity there, but that doesn't mean that we don't have a limit. It depends on where the discontinuity is. All right, let's look at this graph. So first, we just want to take a look at the graph of 2x squared minus 2 over x plus 1. All right, let's take a look. Wait, where's that? Okay, now so they're telling us here the domain is everything from -infinity up to -1, combined with -1 up to infinity. And the range is from -infinity up to -4, combined with -4 up to infinity. Okay. So the discontinuity, this tiny little hole here is the discontinuity. And there's only that one point at which there is a discontinuity. And of course, that's because if x is equal to -1, we have division by 0. Okay, so when x equals -1 up here, we can see that -1, -4 is undefined. Now, the limit that we're looking for, though, um, can be found, as we've seen here, by replacing the existing function with something a little bit simpler after doing a little factoring, and you can see that the limit actually is -4. Now, you might remember from when we start doing limits, you can actually have a limit where there's a discontinuity as long as the limit is the same coming from both directions. And you can see that as the function approaches this point from the larger x's, meaning from the right, we're getting awfully close to -4. And as we approach from the left, the smaller values, the same thing is happening. So that being the case, we can conclude that the actual limit here is -4. In spite of the way the function appears, the limit is -4, in spite of the discontinuity. Okay, great. Now, what else do we have here? Here we go. Let's look at this one. Now, this one leads to infinity over infinity, another of the two indeterminate forms that can be applied with, or can be solved for with L'Hopital's rule. All right, so you can see that direct substitution is going to give us 3 times infinity minus 1 over 2 times infinity plus 1. So all right, now in this case, they're showing us that in spite of that, you can actually work around that by dividing all the terms in the numerator and the denominator by the highest power of x, which is x squared. Okay, so when you do that, we will get a result. In spite of the fact that with the original function, we have an indeterminate form, there is a way to work around that. So what did this accomplish, by the way? Well, you can see what's going to happen is we're going to wind up with 3 minus 1 over x squared divided by 2 plus 1 over x squared. Now, the limits of constants are just equal to those constants. Whereas here, this limit is going to go to 0 because what's happening is that the denominator is getting larger and larger and larger. So that ratio is getting smaller and smaller and smaller, and will actually, the limit, be equal to 0. Same thing here. So we'll end up with 3/2. Okay, so let's once again go back to symbol lab and graph this thing, and you'll see what's going on. 3x squared minus 1 divided by 2x squared plus 1. All right, what does this look like? Remember, we're taking the limit as x goes to infinity. So that means as we're increasing x, now you notice there's an asymptote here. And that asymptote appears to be, it's hard to tell from this graph, but it's 3/2. And so in other words, the function is going to get very close to 3/2 without ever quite reaching it as we increase x up to infinity. So that makes this our limit. Very strange looking graph, but you can see that there's a horizontal asymptote and the function converges that but never actually touches it. Now, in these two cases, direct substitution led to an indeterminate form. In the first case, it was 0 over 0. In the second case, it was infinity over infinity. So we used a technique to rearrange the limit into something which was solvable. And we've seen this in the past. We've done this before. In the first case, we used factoring. In the second case, we divided the numerator and the denominator by the highest power of x. And that worked great. But sometimes it doesn't work out so well. In other words, you might find a limit that gives us 0 over 0 or infinity over infinity, and yet there is no algebraic technique we can use to simplify it. And yet there is a limit. So what do we do about it in those cases? Well, we're going to use L'Hopital's rule. Now, this is a very powerful result, and you'll get a lot of use out of it. And certainly in Calc 2 and 3, it's a very helpful, useful rule. Now, by the way, you see that word, everybody wants to say hospital. It's L'Hôpital. It's a French name, L'Hôpital. Okay. Now, how does that work? Well, imagine yourself trying to take a limit and end up with one of these indeterminate forms. What you could do is, as it turns out, let me find the final result here. Here it is. This is what we're aiming for. If you take the limit of a ratio of functions as x approaches c, and that gives us either 0 over 0 or infinity over infinity, what we can do is take the derivative of f of x and the derivative of g of x, and sometimes that will help. It will reduce it to a simpler form where we can solve with direct substitution. So in other words, the beauty of this rule is that all you have to do is take the derivatives of the numerator and the denominator, and that might give you the result you're looking for. Now, by the way, as it turns out, if this doesn't work, we can try the limit as x goes to c of f double prime of x over g double prime of x. And if that still doesn't work, we can keep going and going and going until we get to the point where we can actually solve for it directly. But this only works, now keep in mind, this only works when we get 0 over 0 or infinity over infinity. For another type of indeterminate form, which we'll see more of them later on, what you will probably end up having to do is rearrange the limit somehow to get it into the form 0 over 0 or infinity over infinity. And once it gets to that form, then we can use L'Hopital's rule. So they've got a good example for us here. Let's say that our function is this. Oh, actually, this is another one of those cases where we can use algebra. So you can see what they've done here. It turns out that e to the x minus 1 divides evenly into e to the 2x minus 1. And then they reduce this to the limit as x goes to 0, e to the x plus 1, and that in turn gives us 2. So again, we didn't need L'Hopital's rule, but here's one where we might. In fact, we do, because if you look at this one, you'll see that you get so this one is eligible to use the L'Hopital's rule. Okay. Now, unless you can come up with some clever alternative strategy, it's probably easier to just go ahead with L'Hopital. Now that we know how it works, before we didn't know about it, so we had to just manipulate the limit until we found something that we can use. Now, as soon as you see that you've got 0 over 0 or infinity over infinity, you might as well go ahead and use L'Hopital's rule because it's really very straightforward. So what would happen here? Now remember, in the numerator, just a quick reminder, the derivative of e to the f of x is e to the f of x f prime of x. So that means here we have e to the 2x minus 1. Sorry, sorry, let's do that again. T dx. So we can break this up into two terms. Now this one just goes to 0. So we end up with e to the 2x times 2 because we're treating that exponent as f of x. So f of x is 2x, and f prime of x must therefore be 2. All right, so in other words, what we're saying here is that in this limit, the derivative of the numerator is 2e to the 2x. Okay, so starting with this is our original limit. So that's 2e to 2x. And in the denominator, of course, the derivative of x is just 1. And so ultimately you end up with 2. Okay, so there didn't seem to be an algebraic way of rearranging this equation into something simpler that where we could actually take the limits directly. Instead, we took the derivatives of the numerator and the denominator, and then we solved directly for the limit. Okay, now that led us to 0 over 0. We could just take in the derivatives again. We didn't need to do that here. In fact, most of the time that won't be necessary, but sometimes it is. So it's good to know that you can take the derivatives as many times as you need, but usually the first time is enough. Then once you get to that point, you can do direct substitution and you should have your answer. Now, once again, we're going to graph this in Symbolab. Let's see, just so you can see what this function looks like and get a sense of where the limit should be. All right, so in the numerator, we had 2e to the x. Minus 1 over x. Now that's a wild looking graph. The limit that we're searching for is the 0. Okay. So it says here, now according to this, that means it's 2. Now, it's very hard to tell from this graph. It really is. But the limit that we solve for is in fact 2. Right about there, I guess. Okay. Now what else do they have for us? Oh, I just realized I typed the wrong function. That might be why the graph doesn't even tell us what we should know. My fault. Sorry. E to the 2x. Yeah. Minus 1 over x. That's my fault. Hold on 1 second. I should have guessed they wouldn't give us one that was such a mess. At least not right away. Well, that's a lot more like it. I think we'll all agree. So they're asking us for the limit as x goes to 0. And you can see, again, there's a discontinuity at the point 0, 2. But again, because the function is approaching that same point from both sides, that means this is, in fact, the limit as x approaches 0. Okay, so now it makes sense. Very good. In fact, it makes so much sense. I'm going to grab this graph and show it in the notes. Okay, so that's what this is all about. All right, L'Hopital's rule, yes. So here they're deriving it a bit. Oh, by the way, they want you to know that I did say before that it has to be 0 over 0 or infinity over infinity. It turns out that actually, with the infinities, the sign is of no consequence. In other words, you can have 0 infinity over infinity, negative infinity over infinity, infinity over negative infinity, or both of them negative. It still counts, right? Um, so in other words, we don't have to pay attention to the sign of the infinities. As long as it's infinity over infinity or 0 over 0, then we can use L'Hopital's rule. All right, let's see. Yes, so this is one we were just working on, and they're reminding us that yes, direct substitution would have led to 0 over 0, which means we're going to need to take the derivatives of the numerator and the denominator, and hopefully that'll make it possible to solve for this with direct substitution, and that's in fact what just happened. Let's see. Here's another one. Let's try this. So this time we're going to wind up with direct substitution. Oh yeah, there we go. Infinity over infinity. That's one of the indefinite forms, sorry, indeterminate forms that will let us use L'Hopital's rule. So where's the derivative of log x? Put that over here is 1 over x. The derivative of x, of course, is just 1. So you've got the same, this is the same thing as the limit as x goes to infinity of 1 over x over 1. So when we have x in the denominator is getting very, very large, that indicates that the limit is 0 as x goes to infinity. All right, now let's go graph this. Now you can see there is a discontinuity here at 0. Let's see what this looks like. Log x over x. All right, so you can see as it gets, x keeps increasing, it's getting awfully close to, if you can visualize it going extremely large, if it is heading towards 0, you can see the slope is negative here. Although it's taking its sweet time, as x increases, the function is in fact converging to 0. You can tell because there's a asymptote here. These dashed lines, as you know, are Symbolab's way of indicating that this is an asymptote. So that's how we know the function is in fact converging to 0. So the limit must be 0. It's always easy to tell just by looking at the graph. The fact that that's an asymptote is what gives it away. Now I mentioned before there are other indeterminate forms that do not let us use L'Hopital's rule. Here's some of them: 0 times infinity, 1 to the infinity power, infinity to the zero, 0 to the 0, infinity minus infinity. So what they're basically encouraging us to do is say, listen, even if we run into one of these, there's a very real chance that we could rearrange our limit algebraically and turn it into something that is going to lead to either 0 over 0 or infinity over infinity with direct substitution. So let's see, what are we doing here? Oh, the first one, oh, I see what they're doing. Okay. So that one is actually going to give us infinity times 0. Well, actually, all four of them would. Oh, I see. They already mentioned it over here. Okay. So what they want you to see is that all four of these can be manipulated into giving us or making it possible to use L'Hopital's rule. Oh, okay. They didn't actually show us how to do it. Let's take a look at these. Sometimes it's just a question of rewriting it a little. It's like this one. Yeah, I think that one's pretty self-explanatory. And the second one is the same thing. Two, these cancel out. So in other words, in spite of appearances, even though all of these lead us to the indeterminate form 0 times infinity, we're still going to be able to find limits, even in spite of not being able to use L'Hopital's rule. Now, this one, limit of x goes to infinity of x over e to the x. Now, this is infinity over infinity now. So if I were to, oh no, it's fine. I mean, it's already infinity over infinity, which means I can use L'Hopital's rule. The derivative of the numerator is 1. The derivative of the denominator is e to the x, and we ultimately end up with 0. Okay, beautiful. And then the last one is the reverse of this one. The limit as x goes to infinity of, let's rewrite it as e to the x over x. So again, direct substitution. All right, great. So when we take the derivatives, oh, okay. Now this one, oh, it is infinity. Okay. I mean, there doesn't seem to be any other option here. It's got to be infinity. I was wondering if there was some other trick that they had up their sleeves. No, it is just infinity. Okay. All right. Now we have, here's a tricky one. And again, you can see where this is going. It's an indeterminate form, but not one of the ones that we can use with, or that we can apply L'Hopital's rule to. So the challenge is to rewrite it in such a way that it is possible to use L'Hopital's rule. So right now, this is going to give us, and that's just going to give us, ooh, this is not going to work. This is infinity over zero. Oh no, sorry, it is infinity over infinity. Okay, so in other words, here the point of this one is that if you rewrite it the way I've done it here, it's now possible to use L'Hopital's rule. Whereas over here, zero times infinity. So the derivative, of course, of radical x will be 1/2 x to the negative 1/2 power. And then that's going to give us, looks like it's going to be zero because you've got a gigantic, infinite, yeah, it's just zero because you've got infinity. The value of the denominator is getting extremely large. And so therefore, you've got 1 over a progressively larger number, and that means we end up with zero. And again, we can graph this just to see what it looks like. 1 over, sorry, radical x over e to the x. Let's take a look at that. Yeah, another one of these. All right, you can see as we move to the right, as x increases, the curve is declining, and you can see that according to the dashed line here, the horizontal axis is an asymptote, which means that the limit as x goes to infinity must be zero. All right. Okay. Now here's an interesting one. Now, this one introduces a very important idea, and that's the idea that you can actually rearrange this, not in a direct way. And by the way, substitution here is going to leave us with that's one of those forms. Yes, one of the indeterminate forms that we cannot apply L'Hopital's rule to. So what do we do about it? Well, now this is a very clever approach. They're going to use natural logs. So you're going to say, well, if y equals limit as x goes to infinity, we can take the natural log of both sides. And that in turn becomes based on the properties of logarithms, we're going to have x log 1 plus 1 over x. Now, this is where it gets a little interesting. They're going to have us do this. Now, this is where it gets really intense. We're going to rewrite it a little bit. Instead of having x in the numerator, we're going to create a ratio where 1 over x is in the denominator. Now, algebraically, these are the same thing. What's the point? Well, Let's see if we let's just solve for this directly with substitution and see where it takes us. So that would leave us with log 1 plus 0 over 0. Now the log of 1 is 0. So that means we can now apply L'Hopital's rule here. Okay. So now that's not going to be easy, but we can do it. So we're going to think of this as f of x is log 1 plus 1 over x. G of x is 1 over x. So f prime of x, it's the chain rule will be 1 over 1 plus 1 over x times the derivative of whatever that is, 1 plus 1 over x. And oh, no, not 1 over x, 1 over 1 plus 1 over x. That's it. All right. So in other words, remember the way the log works is the derivative of the log of u is 1 over u du. Plus c, I mean, not plus c, 1 over u du. All right. So here we've got 1 over, this is our u. The derivative is, keep in mind, this is the same thing as 1 plus x to the minus 1. Okay, so that'll do it. All right, or we can rewrite it as and then g prime is very simple. G of x is 1 over x. G prime of x would therefore be minus x to the minus 2. So the ratio of those two, let's see if we can simplify that. Oh, actually, we don't need this part anymore. Um, all right, so we're getting close. With direct substitution, we'll have 1. Should we? No. What's happening is this is going to 0. So we're left with 1 over 1 plus 0 or 1. Now, we're not done yet, and I'll tell you why, because way, way back, we've kind of lost track of it because we've been working on this part for so long. We actually have log y equals the limit of log 1 plus 1 over x divided by 1 over x. So that means the 1 we just got represents this. So what we can do is replace this with log y equals 1. And therefore, y equals z. And that's the limit, okay? So this actually proves to be an incredibly important result in calculus. The idea that this limit right here, this is in fact the definition of E. Okay, so if you haven't seen it before, this is where E comes from. This particular limit is E. And we just proved it. So we got a lot done there. We not only are learning more about L'Hopital's rule, but we're able to prove why this is in fact equal to E. Okay, well I thought that was kind of cool. I'm sure they did that on purpose. They want you to see this result because it's awfully, awfully important. So there it is, the definition of E. At long last, we've always been told that it's approximately equal to 2.7 something. Well, now you can see where it was taken from. And that's what the graph looks like. Let's see. Now they're going to do, now this one looks like a nightmare. So if we do substitution here, we'll get sine 0 to the 0 power. And, oh, I don't seem to have my calculator right here. Hold on a second. The sine of 0 is it's 0. Right, right. 0 to the 0. Now, of course, that's one of those indeterminate forms that we cannot directly apply L'Hopital's rule to. So that means we need to come up with another strategy. Looks like they're going back to the well with the logs. All right. Based on properties of logs, we're going to have whoops, hold on a second. Okay, well, now in the interior here, we still have a problem because this is, if you directly try to solve this, you're going to wind up with 0 times 0. Actually, it's even worse than that because the log of 0 is undefined. So we got a mess on our hands here. So what do we do? Well, once again, we tried this trick once before. We're going to rewrite it like this. Okay, well, that's kind of better. Oh, no, wait a minute. No, that's going to give us, ah, Oh, I see what they're saying. Okay, so that's going to lead us to infinity over infinity. So now we can take some derivatives. So the derivative of the log of sine of x is going to be 1 over sine x. And if you remember, the derivative of the sine of x is the cosine of x from the chain rule. And that in turn is the cotangent. The derivative of 1 over x is the derivative of x to the minus 1 Okay, so that means we can rewrite this as cotangent x over uh, minus x to the minus 2. Yeah, so that's still going to give us a problem. Oh, I see what those clever people have done. They're rearranging it again. So yeah, the cotangent could be thought of, since the cotangent and the tangent are inverses, we could rewrite this as so just as a note here, cotangent x is this. And so now we're going to take some more derivatives because now we've got 0 over 0. Okay. So then that means that we're going to take the derivatives one more time. Now the derivative of the tangent, we have that chart, which I didn't open up here, so we can get it out of Symbolab. The derivative of the tangent is secant squared x. So now, as far as that goes, now we've got 0 in the numerator. Let's see what the secant. Now remember, the secant is the inverse of the cosine. So we take the cosine of 0. It's 1, and then 1 squared is 1. Okay, great. All right, so just remember that so therefore secant squared of 0 Okay, so the final answer is 1 after all of that work. Oh my God. Yes. Now it looks like in this case, what they're going to actually have us do, we haven't seen this before. Direct substitution leads to 1 over 0 minus 1 over 0, or infinity minus infinity. So they're going to literally have us combine these two fractions. first to see if we can put it into the proper indeterminate form, 0 over 0 or infinity over infinity. Let's see if it works. You never know. Um, that would mean the common denominator. Well, let's try this. And that would be all right. Now let's see what happens if we try to take the limit as x goes to 1. Oh, bad luck. Uh, let's see what we got. All right, well, at least that means we can take this catastrophe and use L'Hopital's rule. Okay, so, well, I'll tell you what. This one's going to be an incredible mess. So let's just skip ahead just a little bit here and see what they came up with. It looks like this ultimately leads to 1 over 2. Okay. Now here, what they want us to do is note that if you have infinity plus infinity, that counts as infinity, and that is it's defined as not indeterminate but determinate, meaning we can find a solution. Negative infinity minus negative infinity is negative infinity, any way you look at it. That's a determinate form. 0 to the infinity is just 0. 0 to the negative infinity is considered to be infinity. So with those, we don't need to worry about L'Hopital's rule because we actually have an answer. So here, for example, they want us to try L'Hopital's rule on this one. So let's first of all see what happens with direct substitution. Well, all right then. So that means we can use L'Hopital's rule. It's just infinity. Okay, because if let's quickly look at this function in symbol of e to the x over x. Well, you can see yes. As x increases, the function increases without bound, and therefore the limit is infinity. Yeah, another one of those bizarre cases, but that's what it looks like. All right, so we have 2 knowledge checks here. Now, after this, what they're going to do here is you're going to give us a pretty comprehensive set of rules for derivatives and integrals they're going to try to start tying together everything we've done in this course really into a few charts, which is super helpful because everything's together in one place. We'll see what's happening when we get there, but for here, we're just going to wrap up these last two knowledge checks. This is, by the way, section 5.6. Okay, so when these two are done, I think we're past our time, so we'll stop here for this session. The next session, we'll move on to 5.7. We're going to start to see a large number of rules for differentiation and integration, and we're also going to bring back not just trig functions, but inverse trig functions. So they have derivatives and integrals too, so we have to know them all. All right, here we go. Here's our first knowledge check. So first, let's try direct substitution. Great. So we can use L'Hopital's rule. Now, the derivative of x, of course, is just one. Based on the chain rule, e to the 3x. So we're going to wind up with the limit of one over 3e to the 3x as x goes to 0. Now, e to the 0 is just 1, so we end up with 1/3. All right, that would be b. All right, now let's try this one. Oh, well, that looks a lot like the one we had earlier, doesn't it? And that would be this limit x goes to infinity of e to the x over radical x. All right, so this is the other indeterminate form that lets us use L'Hopital's rule. Now, radical x, of course, is the same thing as x to the 1/2. So we've got the limit based on L'Hopital's rule of e to the x over this. Now, that's kind of a mess. And then we can write that as and it's just infinity. Or D, the limit does not exist. Okay, it means the same thing. Okay, so that's that. So let me just quickly show you what's coming up in 5.7. Here it is. Already with the inverse trig functions. So they're going to remind us how these work. Now, what's interesting about the trig functions is that they do have a derivatives, but they're only defined over very narrow ranges. So we have to be very careful with these. So they're going to run through all of this with us. And they have the graphs here. So we'll dive into this next time. All right. So, all right. I think now that was a good session because that L'Hopital's rule is, I'm telling you, is going to be so important throughout the rest of this course and Calc 2 and 3. So it's good to have it, some expertise in it now. And then here we can sort of veer off into the area of inverse trig functions. And you can see these graphs. This is getting very involved. But and then they're going to start introducing some formulas. So we have all of them in front of us when we need them. And they're even going to go back and review what we learned about differentiation way back in the beginning of the course. So you have it all again in one convenient location, which is kind of nice. And then the same thing's going to be true in the next section as well. So this is where we're headed. So for now, we'll stop it here and then we'll pick it up next time with our inverse trig functions. So I'll see you then.